Hi everybody, welcome to Chem 103 again. It is Tuesday and I'm in room Z310 if you're on campus looking for me to do this. So today we're going to be looking at drawing chemical structures, and today we're going to focus on just the basics of what these things look like. We've seen some chemical structures already, but we haven't really talked about what those things mean. I know a lot of you had questions like in the chromatography and dyes lab, it asked you to compare some structures, and there were a lot of questions like, what does this even mean? We haven't talked about this yet. So that's what we're going to focus on now. Hopefully the stuff with chemical equations and atoms went well last week. I look forward to seeing your module reflections about that. All right, so let's look at chemical structures. Now, you could probably assume, or we've talked about the drawing atoms. So you just draw, C, H, O. You draw the letter that stands for an atom. Multi-letter atoms, well, two-letter symbols, have a capital first letter, lowercase second letter, and the actual names of the elements are not proper nouns, so they don't have uppercases. But we draw these kinds of symbols as representing those atoms. Sorry, I'm not thinking straight today for some reason. All right, so now what happens when we connect these into compounds? Now there's two broad types of chemical compounds. We have ionic compounds and we have covalent compounds. Ionic compounds, we're not really going to deal with much today. They are where we have two charged particles like sodium and chloride. So the compound would be sodium chloride, and they simply attract each other because positive and negative attract. So that electrostatic attraction happens here, and you end up kind of forming this cage-like structure or lattice, whatever you want to call it, of a bunch of packed ions, sodium cations, positive ions, and chloride anions, negative ions. We're going to talk about ions in, I think, the next unit, maybe in 2 units. But for now, you can just sort of file that away in your head that that's a type of chemical compound. What we're going to focus on this week is these covalent compounds where atoms actually share electrons with each other. So this is probably what you're more used to seeing with chemical compounds, is this like line in between two atoms. So something like that, or like water kind of has this sort of structure. And so these lines that we draw are called covalent bonds, and they represent two shared electrons. So those two atoms share electrons, and they're then bonded. They're really just close enough that those two electrons can occupy both atoms. And when we get into electronic structure, we'll understand that term a little bit more when we talk about valences. But for now, just know those lines are two shared electrons. You can also have compounds with 2 or 3 bonds between atoms. Like these, that's formaldehyde. This is carbon monoxide. That would be considered a double bond, which is 4 shared electrons. And this is a triple bond, which you can probably guess is 6 shared electrons. If you want to access this stuff, by the way, it's all in the class notebook. If you're having trouble with finding any of this stuff, please let me know. Either send me messages or come see me in class so that we can get you set up and make sure you're not missing anything. All right, so those are our different types of bonds that we're going to deal with today. And so I'm going to tell you a little bit about how to put these structures together. And the goal today is, can we take something like this, which we call a molecular formula, a formula that tells you how many of each atom there are, and can we turn it into an actual structure? Can we draw those connections and build something? All right, so in order to do that, we need to know a little bit more information. In the future, when we learn about the electrons and things, you'll be able to come up with some of this stuff on your own. But for now, it's going to be helpful if we just set down some rules that we're going to use. So we're going to mostly focus on organic compounds or organic chemistry. I was thinking chemistry in my head and I said compounds. Organic compounds are based on carbon, meaning they are mostly made of carbon atoms generally, but they also have everything else, particularly hydrogen, oxygen, but then, I mean, they can have most other things on the periodic table as well. You've probably heard that term organic chemistry, something like that. Where that comes from, organic means relating to organisms, relating to life. Back long time ago, it used to be thought that there was an absolute separation between the chemistry of life and the chemistry of inanimate objects. So chemicals that came from living things would always be only made by living things, and chemicals that came from rocks and things like that would always be there, and there wasn't ever any overlap. We know now that's not true, that chemicals are chemicals, organic compounds are produced in rocks and in space and things like that. Inorganic compounds that we think of as rocks are in our bodies as well, so there's all kinds of crossover, but the name has stuck, and just now it means more of these carbon-based compounds that do tend to have important consequences for living things, like molecules that interact with living things. All right, so we're going to focus on organic compounds. And one nice thing about organic compounds is they have some fairly predictable behavior in terms of how the atoms bond together. So we're going to make a little table, and the number of bonds that atom usually makes. And we'll start with carbon. So a carbon atom is generally going to connect to four other things. I know I actually used one of the exceptions up here where I have only 3 bonds between carbon and oxygen in my triple bond example, but generally we're going to see carbon making 4 bonds. So that means when we look at a structure and we try to decide, is this a chemically reasonable structure, is this something that could exist, we're going to look at the carbon atoms and make sure that there's 4 lines coming out of them. Those could be to 4 different atoms, those could be multiple bonds to just a couple atoms, but we're generally going to want to see 4 bonds. Now, this being chemistry, is that some absolute rule that you can use in every possible situation? No, it's not. There's always exceptions, there's always ways this doesn't work, but for our purposes now, this is a helpful rule to think about. Similarly, hydrogen tends to just make 1 bond, which means that if you have a compound that's made of just carbon and hydrogen, so let's say we want to know a formula for C3H6, all right? What that tells us is that we have 3 carbon atoms and 6 hydrogen atoms, and we have to put them together in a structure, and we have to follow these bonding rules that we just put up. So we take our 3 carbons, we take our 6 hydrogens, and we have a lot of options of how to connect them, but let's look at some things that don't work and talk about why they don't work. So what if you put a hydrogen in between 2 carbons? Why doesn't that work? Well, it doesn't work because this hydrogen has 2 bonds, 1, 2. And so that's not going to work because our rule says that hydrogen can only make 1 bond. So another way of thinking of that then is that hydrogen has to always be on the outside. Right? It can't be inside in between other bonds. That also tells us that the carbons all have to be connected to each other, because otherwise there would be a hydrogen in there with too many bonds. So we can use those rules to logically figure out that the carbons have to be connected together. Then we can add the hydrogens in, and to know how many hydrogens to add or where to add them, we again look back at these rules and we say, okay, well, each carbon needs 4 bonds. So I'll start with one of them, and I'll start adding hydrogens around. Oh, one of the lights in the room just shut off. I hope you can still see me okay. And then that's taking care of 3 of them. I've got 6 total, so I got to add 3 more. So we'll go 1, 2, 3. And so you can see where I came up with those placements was I said, all right, oh, now the lights are very off. I look like I'm, here, let me see if I can fix this so I don't look ridiculous. That kind of looks cool. It's very shadowy, but that'll work. So I've got, yeah, maybe take that down a little bit more. The camera, I think, keeps compensating for the brightness. Where was I? Okay, so each of these carbons now has 4 bonds, 4, 4, but the one on the right doesn't. So that tells us something's wrong here. This isn't working. This isn't the right arrangement because I couldn't fulfill the 4 bonds on that carbon. So I got to try something else. I know I can't add any more atoms. I've used my 3 carbons. I've used my 6 hydrogens. So how can I get to a structure that fits the rules without adding any more atoms? And the answer is I have to, I have to use multiple bonds. So if I take this hydrogen off here, well, okay, hold on. Before I do that, so what if I just add another bond here? I'm getting closer, but now not only does this carbon only have 3, but the one in the middle now has 5 bonds. 1, 2, 3, 4, 5. So that's not going to work. So we can't do that. But what we can do is we take this hydrogen off and put it over here. And now look, every carbon has 4 bonds. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So this is a reasonable structure for C3H6. There's actually another one that works also. Well, we could put the double bond on the left side as well. That ends up actually being the same molecule because you just flip it over. But the other different compound that works is if we connect all those carbons in a ring, or I guess it's really a triangle if there's just 3, and then we put 2 hydrogens on each carbon. Now again, each carbon has 4 bonds, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. But the overall structure still just has C3H6, and each hydrogen only has 1 bond. So that works. So you got to fit these rules always when you're trying to figure out if a structure is chemically reasonable or not. Okay, so let me give you a couple other rules. Oxygen is generally going to make 2 bonds. Nitrogen usually 3. The halogens, which is fluorine, chlorine, bromine, and iodine, are generally just going to make 1. Just like hydrogen. And you can make similar predictions for some of the other, oh, I can't even see the periodic table, it's so dark in here. For some of the other atoms as well, like oxygen makes 2, so the other atoms underneath are also going to make 2. But for the compounds we're seeing, these should take care of it, and these should tell us everything we need to know. All right, so that said, let's try to make some compounds. So we'll start with, well, we'll start with the one that I said earlier, because I said that was a goal, right? C3H6O. Yeah, if you're watching this not live, pause here and try it and see if you can come up with a structure for C3H6O. See how many different structures you can come up with for C3H6O. And then come back and see some of the ones that I made. So C3H6O, we've got these atoms. We've got 3 carbons, 6 hydrogens, and an oxygen. And we have to put them together in a way that fits all of these rules. So we want to make sure whatever structure we draw, each carbon has 4 bonds, each hydrogen has 1 bond, and each oxygen has 2 bonds. If we do that, we should have a reasonable structure. All right, so we're going to use some of the same ideas that we did before. We know the hydrogens can only have 1 bond each, so we can't really build our main structure of the molecule using the hydrogen. We have to just kind of put those on the outside later. So maybe we just start simply and put CCCO. okay? And then we'll start filling in some hydrogens and see what we can get. So we need to add 6 hydrogens to this molecule. 1, 2, 3. Again, I'm filling the carbons to 4 before I'm moving on to the next one. 4, 5, and then 6. All right, and now you should notice a problem, that this carbon only has 3 bonds, the one on the right, and the oxygen over here only has 1 bond. And we want each carbon to have 4 and each oxygen to have 2. Well, when we have 2 atoms that both need more bonds right next to each other, that's actually a pretty easy solution. We can add that double bond, and that works. So we'll go back and double check it. Each carbon has 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Good. And then each oxygen, well, the only oxygen has 2, 1, 2. Now there's lots of different possible structures for C3H6O. That's just one of them. We could have connected the oxygen to the middle carbon like this. All right, that would work as well. We could also not have the oxygen on a double bond to carbon. You are going to find that you need a double bond here somewhere, or again that ring structure. But we could do something like CCOC with a double bond here and something like that. That would work. If we want to do a ring structure, we could put the oxygen in the ring and make like a square, kind of like that. We could also add the oxygen outside of the ring. The oxygen could end up with a hydrogen attached to it. That will also work. So there are lots of different possibilities. If you want to try to challenge yourself, see how many different structures you can come up with that same formula. But these are all we would call chemically reasonable structures. They may not all actually exist in nature or synthetically. There may be reasons why a particular structure you draw can't exist. But if we've followed those bonding rules, we should have a structure that is at least chemically reasonable. All right, I'll put up another one for you to try. Oops. See if you can come up with a structure for C6H13NO. All right. So that is, what's going on here? That's the basics of this type of structure. And the name for all of these kinds of structures is Lewis structures, after somebody who first developed them. So when we draw the atoms and then the lines connecting the other atoms, those are called Lewis structures. But as molecules get bigger and bigger, we're going to find that Lewis structures are kind of inconvenient. It's annoying to draw every little thing out all the time like that. It also doesn't give us a good sense of angles. We could, draw things with correct angles in Lewis structures, but for all of these reasons, we're going to look more often we're going to use some different types of structures. And today we're going to talk about condensed structures, and then on tomorrow, Wednesday, we're going to talk about line structures. So let's start with condensed structures. Condensed structures are just a way of shortening up the structures so that they're a little bit quicker to draw and easier to type on a computer. So let's take C3H8, which the Lewis structure would look like this. This one doesn't have any double bonds. So we could draw a Lewis structure for C3H8, or we can condense it. And the reason we can condense it is because now we know something about these structures. We know that carbon needs 4 bonds and hydrogen needs 1. And so the condensed structure looks like this. There's actually a couple different ways to draw it. But what we've done here is we've condensed the hydrogens onto their carbons that they're connected to. So we have, instead of drawing out every hydrogen, we've condensed them. And then beyond that, we've also condensed the bonds between carbon. We just kind of smushed them together. But as I said, this requires us to know a little bit about structure, because if you're just looking at this condensed structure not knowing anything, you might think this means that we have a C, and then 3 hydrogens, and then a C, and then 2 hydrogens, and then a C, and then 3 hydrogens, you know, and that's not what that means. We know that's not what that means because we know that carbon has to have 4 bonds and hydrogen has to have 1 bond. But that's what I mean. You need a little bit of chemical knowledge to be able to interpret these. So now that we know that these two are the same, that the Lewis structure and the condensed structure for C3H8 show the same structure. Sometimes if a structure is kind of branching and has like all kinds of interesting shapes there, it's more useful and helpful to have the condensed structure still have some lines in it. So it's also a condensed structure to draw it like this, to not actually smush it all together. And that's also a condensed structure. So let's take some of the ones we did over here and draw some condensed structures, and we'll also see what some of the drawbacks are to doing that. All right, so let's look at this one in the upper right. If we wanted to draw a condensed structure for that one, what I always recommend first is leave the basic structure alone and just condense the hydrogens. Then, if you want to actually smush it all together more, you can do that. So if we're just condensing the hydrogens here, you can see that this first one has 2 hydrogens attached to it. So that's going to be CH2. Then we've got a double bond to CH, and then O, and then CH3. So that would be a condensed structure. And if we wanted to smush that down even more, we could just write CH2, CHO, CH3. But let's think about like going the other direction on here though. So let's say we had, let's say we wanted to go the other direction, meaning let's say we have this structure and we want to draw a Lewis structure of that. So we have to kind of expand it out. So we're going to do this backwards. Now, if I didn't know already that it had a double bond in it, I wouldn't necessarily know what to do here until I drew it all out. That might still look okay to me until I actually start doing the Lewis structure stuff. And that's when I would notice that 2 of these carbons don't have enough bonds. And then I would say, oh, aha, okay, I have to add another double bond there. So there's a double bond in this structure. So by smushing this thing down into a condensed structure, you're definitely sometimes making it a little harder on the person you're communicating it to. But if that person has some chemistry training, they should be able to tease that out and figure out what that means. All right, let's look at this one. What happens when we have a branch structure like this and we want to make a condensed structure of that? Well, we start the same way. So this one's going to be CH2, C, CH3, OH. And that's fine. We could just leave it like that. That's a condensed structure. But if you really wanted to smush it, you would use parentheses. So you could go CH2, C, and then parentheses OH, and then CH3. And that's telling us that the OH is coming off of this C. You see how that works there? Okay. So then let's look at where it doesn't make sense to kind of smush it necessarily. So let's take a look at this kind of square ring looking one. If we look at this one and we want to make it a condensed structure, we can still condense the hydrogens and we can go CH2O, CH2, CH2 like that. But it really doesn't make there really isn't a good way to actually smush that in all the way down to just being on a straight line, because there's not a good way to communicate that that's supposed to all be connected in a ring. So sometimes it just doesn't work well to do that full condensing of the structure, and it makes more sense to leave some of the lines in, like we see here. Okay. So let's do a couple for practice. So see if you can draw a condensed structure of this one, and then I'm going to write a condensed structure, and you try to draw the structure. All right. If you're watching later, go ahead and pause the video here so that you can give those a try, and then come back when you're ready. Okay, so for the first one, we're going to first condense the hydrogens down onto the carbons. So we have CH3, CH, CH, CH2, OH. And oh, you know what? I should have drawn that out a little bit more. Really, in a Lewis structure, you shouldn't have any of those condensed abbreviations. So that would be a reasonable condensed structure here in blue. And then we could also shorten that even more. We could go CH3, CH, CH, CH2OH, but now we don't communicate that double bond information, and we leave it to whoever we're trying to show this to communicate that. Another way you'll also see condensed structures is just that information shown. So they might put just the double bond in just to make it a little bit clearer, but leave everything else as it is. All right. Again, as I said before, there's no absolute one correct type of condensed structure. These are all just ways of condensing the structure. So a condensed structure could be any of these. So if I ask you to draw a condensed structure at some point, that's what I'm asking. Just draw one of those, any of those. The reason we go through all the different types is because what you want to be able to do is decode the condensed structure so that you know how that molecule is actually connected. When we start talking about our biodiesel molecules tomorrow, you'll see that it's going to help a lot with those giant molecules to be able to do these condensings. All right, so this one starts in a kind of an unusual way, something we haven't really seen, which is CH3 taken twice. So what does that mean? Well, we could start by doing it like this, but we'd quickly run into a problem. Hopefully you see it here, that this carbon has 5 bonds now. 1, 2, 3 from the 3 hydrogens, and then 4 and 5 from the other 2 carbons. So that can't be right. So what this means is that these two CH3s, 2 carbons with 3 hydrogens, are actually both connected to the next carbon. So those parentheses have to go like this. And I drew them kind of at an angle, but you could just draw them straight up and down, or one over and one down, doesn't matter. That is fine. But that's what that means. And I didn't tell you that that's specifically what that parentheses notation means, but if you tried to do this, like if you tried to draw this structure that I drew first, hopefully you would notice that there's a problem there, and you'd have to go back and revise it. So now that we've got that, we can put in the rest of it. And now that we've got all that, we can turn it into a full Lewis structure by drawing everything out properly. So something like that, and then, hello? Hey, I'm live online.
Oh, I'm sorry.
That's okay.
You want me to shut these off?
No, they turned off by accident. All right, so let's do this again. Sorry, somebody came in there. Okay, there we go. So now we've got a Lewis structure from that. And that's actually it. So I'm done. So practice these. There's lots of good materials in the files section where you can practice drawing these structures. If you want more practice as well, let me know. Tomorrow we're going to take this one step further to line structures, which are the things like you saw in that dyes lab. So where you don't actually show the carbons or the hydrogens at all, you just draw these lines. And we're going to talk about how to do that and how to work through that. So give this a try before tomorrow, and then come back same time. We'll be in room Z351 if you want to join us. Otherwise, see you in lab or see you next Monday for the other folks. Bye.